PU2 aspirants, so your midterm exams are ahead and yes, chemistry exam is there. So in this video, I'm going to discuss the most important questions from all the chapters that is there in your midterm portion. So whether you have studied anything or not doesn't matter. At this last minute, you must revise these chapters, these topics, these questions so that you can get a better score. Okay, so let's get started here. So first of all, we will be having these chapters in the list: solutions, electrochemistry, coordination compounds, DNF block, haloalkanes, alcohols, phenols and ethers. Now remember, this session includes only the most important questions. Okay, coming to the first chapter, that is solutions. First of all, you should know what is Henry's law and how to write its mathematical form and what is the significance of Henry's law. So yes, I have given the answer. So what is Henry's law? Henry's law tells you that when you apply, the solubility of a gas is directly proportional to the pressure over it, right? So this is the what I'll say definition. You have to mention the mathematical formula, and then what is the significance of the Henry's constant? It is used to, or I can say that when the Henry's constant is more, the solubility will be less. Okay, so please prepare this question. Second, okay, before moving forward, here is something very, very important for all of you. So we have launched our KC90 crash course. This is a 90-day offline classes to crack both KCD and COMEDK 2026 examination. So here you will be having offline classes across 8 Diksha campuses. So complete coverage of syllabus will be there for PU2, for KCET as well as for COMEDK. Apart from that, there will be so many part tests and full length tests to check your or to track your progress. Okay, so if you want to join this crash course, you can call on this number or the link is there in the description section. Please go there. You can visit the website, check all details, and then can fill the enquiry form. There's an enquiry form in the website. The link of that is there in the description section. Once you open the enquiry form, once you fill the enquiry form and submit, our counselor will call you back. Okay, so these are two ways how you can take this course. Very, very important. Do try it. Now let's move to the second question. We have Henry's law done, then we have Raoult's law. Okay, so same thing you have to do here. What state Raoult's law and gives its mathematical formula. Okay, what is vapor pressure? Then vapor pressure of CH, Cl3 and CH2, Cl2 are given here. Which is more volatile? Okay, so first of all, let us see what is Raoult's law. So Raoult's law says that in a solution, if you are having two volatile liquids, the partial pressure of each component is proportional to its mole fraction. I'm not going to explain here in much things here. This is just a list of questions that you should be revising quickly. Okay, so here it is there. Next question, what is vapor pressure? So vapor pressure, how will you explain? Or vapor pressure is the pressure exerted by the vapors on the liquid surface. Vapor pressure is the pressure exerted by the vapor on the liquid surface when the system is in equilibrium. Okay, this is about vapor pressure. Next, if you see, the vapor pressure of CHCl3 is 200 and that of CH2Cl2 is 415. Then which is more volatile? So you can see CH2Cl2 will, because it is more volatile, it is able to create more vapor pressure, right? So that is why, which is more volatile? CH2Cl2. Okay. Moving to the next question here, write the expression to relate the cryoscopic constant and the change in the enthalpy of fusion. Okay, so this is there. Take RTF square M by delta by 1000 into delta H of fusion. Each term is explained here. The similar question can also be asked for KB. Okay, so if KB is there, what you have to do? RTB square by M divided by 1000 into delta H of vaporization. Okay. Next we have question number 4. Draw a graph to show the variation of vapor pressure of the solvent and solution with respect to temperature. Okay, vapor pressure of solvent and solution, if that is changing. So here this is the graph to show the vapor pressure of solvent and solution, how it varies with temperature. Okay, that graph you have to draw. Next, we'll see difference between ideal and non-ideal solution. So I have given here 3 points. Obeys Raoult's law. does not obeys Raoult's law. H mix is equal to 0, not equal to 0. V mix equal to 0, not equal to 0. AB interactions are equal to AABB, not equal to AABB. So these are 4 points, and the 5th point that you can add here is examples. Okay, just add the examples for ideal solution and non-ideal solution. Next difference between is for the different types of non-ideal solution, that is positive deviation and negative deviation. Positive deviation, what happens? AB interactions are weaker than AABB. In negative deviations, AB interactions are stronger than AABB. Now here the total pressure is more than the calculated value. Here the total pressure is less than the calculated value. H mix is greater than 0, less than 0. Here you can add one more point. Yeah, just a minute. Next, one more point you can add, delta V mix is greater than 0, and you have delta V mix less than 0. Okay, next, okay, this point we have already written. Example here, ethanol and acetone is there. Here phenol and aniline is there. Okay, next question is about azeotrope and their difference between. Okay, so for maximum boiling azeotrope and minimum boiling azeotrope, so maximum boiling azeotrope shows negative deviation, minimum is shown by positive deviation, and you should be knowing their example. These 2 points are enough. Okay, next, what is reverse osmosis and give its application. So first of all, this is again you have to first explain what is reverse osmosis. We know that what is osmosis. The opposite of that will be reverse osmosis. Osmosis means what? When the solvent particles flow from a lower concentration to a higher concentration solution through a semi-permeable membrane, right? And to stop this osmosis, we apply a pressure called as osmotic pressure. Right? Now, when you apply pressure more than osmotic pressure, the solvent particles start moving from lower concentration side to higher concentration side in the opposite direction, right? So that is called as reverse osmosis. So you can see here, when a pressure more than the osmotic pressure is applied on a concentrated solution, solvent flows from the concentrated solution to dilute solution through a semi-permeable membrane. This phenomenon is called as reverse osmosis. Okay. Then what is its application? It is used in the desalination of seawater. You can just write down this much. Okay, this thing is not required. This is just for understanding. You need to know which membrane is used. Cellulose acetate is used here. Okay, and if diagram is asked, you can even draw this diagram and explain the concept. Next, we'll move to some numerical questions. 1 gram of a non-electrolyte solute. So let me just note down the values that is given. Non-electrolyte solute. So I can write W here is 1 gram. Okay. Dissolved in 50 gram of solvent. W of WB, this one, right? So what is WA here? 50 gram of the solute. Okay. Lowered by the freezing point. So what is delta TF? Delta TF is 0.4 Kelvin. Okay. Next we have freezing point constant. Kf value is how much? 5.12 Kelvin kilogram mole inverse. Okay, though we have to calculate the molar mass of the solute. So I have delta TF is equal to Kf into given mass by molar mass into 1000 by WA. Okay, this is WB. Now, what is delta TF value? 0.4, Kf is 5.12, WB is 1, M I have to calculate 1000 and WA is 50. Okay, so now if I solve this and calculate the value of molar mass, it comes out to be 256 gram per mole. Okay, moving to the next question. The boiling point of benzene is 353.23 Kelvin. So let us note down the value. TB is how much? 353.23 Kelvin. Okay. When 1.8 gram of a non-volatile, non-ionizable solute was dissolved in 90 gram of benzene. So what is the mass of the solute? 1.8 gram. Mass of the solvent 90 grams. Okay. The boiling point raised to 354.11 Kelvin. Okay. Now what happens? Calculate the molar mass of the solute. K is how much? 2.53 Kelvin kilogram mole inverse. Okay, this is there. Okay, now we have to calculate the molar mass, very similar to the previous question, just a slight change in formula. We have delta TB is equal to Kb into molality. What's the formula for molality? Given mass of the solute, that is Wb, by molar mass of the solute into 1000, right, by the mass of the solvent. Okay, all the formula I have written, all the values I have given. Just now what you have to do, substitute it. So let's substitute. Delta TB will be what? This minus this. So I can write 354.11 minus 353.23. Then Kb value is how much? 2.53. Wb value is 1.8. Okay, and then Mb I have to calculate into 1000 by Wa is 90. Okay, now if you solve this, you can find the value of Mb here. Okay, so once you calculate this value and get the value of Mb, you will get around 57.27 gram per mole. Okay, let's see the next question here. Calculate the osmotic pressure in pascals exerted by a solution prepared by dissolving 1 gram of polymer of molecular mass 1,85,000 in 450 ml of water. And the temperature is actually, this is 37 degrees Celsius. Okay, so let's do this. First, what I have first is mass of the solute, so that is 1 gram. Then I have mass of the molar mass of the solute, which is 1,85,000. Then I have here volume of the solution, which is 450 ml. And then we have temperature here, which is 37 degrees Celsius. So 37 plus 273, it will be added, right? So I have here that is equal to 310 Kelvin, right? So now if I just solve this one, we have pi is equal to C into R into T. Now here R value is very important when it is in pascals. So 8.314 into 10 to the power of 3 liter Pascal mole inverse Kelvin inverse. Okay, not 1 second, PA. Okay, so now let's substitute this one. So C value is 1 by 1,85,000 into 1000 by volume 450. Okay, then I have here 8.314 into 10 to the power of 3. Temperature is, we have 37 plus 273, that is 310 Kelvin. Okay, now once you solve this, how much we will get? If I solve this, we will get 30.9 Pascal. Okay, now coming to the next question, vapor pressure of benzene is 200 mm of Hg. Okay, vapor pressure of benzene. So I'll write P0 of benzene is how much? 200 mm of Hg. Okay, let's move forward. When 2 gram of a non-volatile solute, okay, 2 gram of a non-volatile solute, so mass of the solute is 2 gram, is dissolved in 78 gram of benzene. So what is the mass of the solvent? 78 gram of benzene. The vapor pressure is now 195. So what is the new vapor pressure of benzene? 195 mm Hg. Okay, calculate the molar mass of the solute. Molar mass of the benzene is already given. So this is relative lowering of vapor pressure. Delta P by P0 is equal to P0 minus P by P0 is equal to XB, which can be written as NB by NA, right? Again, NB by NA we can write as WB by MB into WA by MA. Okay, so now let's substitute. What is P naught value here? 200, 195 divided by 200. Okay, NB, number of moles of the solute. What is the solute here? That like it's a non-volatile solute. So 2 gram divided by X, and here I have 78 and 78. Both given mass and molar mass of the benzene WB is there, and molar mass is also 78. So now if I just solve this, I get 5 by 200 here, and I'll get 2 by X here, right? So now solving this one, X will give me 80 grams per mole. So what is the molar mass of the non-volatile solute? 80 grams per mole. Okay, fine. So now I'll go to one of the easiest chapter of inorganic chemistry. Electrochemistry is also there, but it's a little bit tougher chapter. So if you want to just revise at the like when you are just revising, first revise all those things which are easy for you. Okay, so let's move for coordination compounds. The first question here are some definitions that you should be preparing. What is a chelating ligand? What is a homoleptic ligand, heteroleptic, and ambidentate ligand? These 4 definitions are very, very important. You should prepare that. So I've given here definitions. So what is chelating ligand? When you have one ligand which is having more than one more than one donor sites, and it forms a cyclic structure with the metal, that is called as a chelating ligand. This is there. Next, homoleptic ligands. If all the ligands are equal, then it is homoleptic. Next, we have heteroleptic. If we have different ligands attached to the one metal, then it is heteroleptic. Then what is ambidentate ligand? A ligand which is having 2 types of donor sites. Okay, a molecule or an ion which has 2 donor atoms to form 2 coordinated bonds with the, okay, so this is the definition for didentate ligand. Now what is ambidentate ligand? Let me just note down. I'll cross this one. 1 second. Okay, so how can we explain a ambidentate ligand? A ligand, see, a ligand which has, okay, a ligand which has 2 donor sites but any one binds to the metal at one time. Okay, means it also has 2 donating sites, but both of them will not form a bond. If both of them are forming bond at the same time, then it is a didentate ligand. It is not a ambidentate ligand. So here you have example of 1 second. Okay, so here we have example of Cn minus. You can have NO2. You have SCN minus. So in Cn minus, CNN both can donate. In NO2, NNO both can donate. In SN also, SNN both can donate. Okay. Next question, for second question here is draw the isomers of PtCl2 and this 2. Okay. So this isomer is very important, PtCl2 En2. So it will have cis and trans form. So see here, first one if I draw PtCl2 En2. Okay, so you have cis and trans form. First I will draw the trans form. Okay, so I have Cl like this, and then you have En is denoted like this. Okay, so chlorine are on opposite side, so this is trans geometry. Now how can I draw the cis one? Cis one, you can just take chlorine on 2 sides and then En on 2 sides. Okay, and now if you draw its mirror image, okay, that Pt is there, I'll draw its mirror image like this. Okay, and then you have here okay, so this is the cis form of that. Okay, so this is the trans form and this is the cis form. Now we have COEN3. Okay, so if I see for numbers 2, that is COEN whole 3 2 plus. Okay, so you can draw like this. This is one En, this is another En, and this is another En. So this is what this is one geometry, and its mirror image you can draw like this. Okay, so this is the I can say one isomer and its mirror image. Okay, next question is also on isomer. You have to draw the isomer of this one. Okay, so remember this example. If you have MA3B3 type, you will get facial and meridional isomers. So I have given here, this is the facial one and this is meridional one. Okay, next let's see question number 4, postulates of Werner's theory. Very, very important question. 3 marker, it can be easily asked. It can be also asked in 2 marker, 3 marker. So in 3 marker, what you have to write? All the 3 postulates. The first postulate is what? It shows 2 types of valences, primary and secondary. In the second point, you have to write what is primary valences, that is normally ionizable and is satisfied by negative ions. Secondary valency, non-ionizable, satisfied by both neutral and negative ligands. Okay. Next we have these type of structural isomerisms. Okay, if any type of this isomerism can be asked, you just have to write the definition and one example you have to give. Okay, so let's see, the first one is with the first one is with linkage isomerism. If you see, linkage isomerism is only possible in case of an ambidentate ligand. So suppose this complex is there, here N is binding with cobalt, the linkage of this one can be written like this, NH3 whole 5 ONO Cl2. Okay, so linkage isomerism arises in a coordination compounds containing ambidentate ligand. Now you see there at that time N was linked, now oxygen is linked. So that is why this is a linkage isomerism. Next, talking about ionization isomerism, this form of isomerism arises when the counter ion in a complex salt is itself a potential ligand and can displace a ligand which can then become the counter ion. So now what is it saying is, the ion which is present outside the complex, that is called as counter ion. Okay, now when you have something inside the ligand, which means something inside the complex which can also behave as a ligand or as a counter ion, then you can exchange this one. So if Br goes out inside and SO4 comes outside, we will get a ionization isomerism like this. Then another 2 form of structural isomerism we have. What is that? Solvation isomerism and coordination isomerism. So what is coordination isomerism? This type of isomerism arises on the interchange of ligands between the cationic and anionic complexes. Okay, so if you see here, I have one complex where cobalt with NH3 is there and chromium with Cn is there. Now if I exchange this one, chromium takes NH3 and cobalt takes Cn, then we will get another form of this complex, or this is the which is called coordination isomerism. Next we have solvation isomerism. Here what happens, just it is very similar to ionization isomerism, but here you have to just exchange with water molecules. You can see 6 water molecule and 3 chlorine was there. What I can do is I can take one water molecule outside and then it will become a, and one chlorine if I bring inside, that will again become a hydration isomerism or solvation isomerism. Okay, next question I'll see on explain the hybridization, magnetic property and geometry of CONH3 whole 6 3+. This is a very important question. There are 4 compounds in the book. What are they? One is this one, another you have COF6 COF6 3- is there, and you have one more compound, that is NiCl4 2- and NiCN NiCN4 2-. Okay, so these 4 compounds, anything can be asked, but there is a high chance of these 2 compounds being asked. I'll explain for this one, you have to practice for other 3. Okay, it is there in the book. So first, what is there? What's the oxidation state of cobalt here? Cobalt oxidation state is +3. What is the electronic configuration then? 3d6, right? You can draw like this, 3d6, 1 2 3 4 5 and then 6. Now what happens? What is the, you have to talk about ligand here. Now NH3 is a strong field ligand. So what will happen? So pairing of electron will take place. Pairing of electron takes place. Okay, now see this ligand, how many ligands are there? 6 ligands are there, so it tries to form 6 bonds with the metal. So what will happen? We need here total empty orbitals, 6 empty orbitals are required. So I have 3d, 4s and 4p. So if I have 3d here, okay, now if I pair them all, so I will have, so I'll get 2 vacant orbital here, 1 vacant orbital here and 3 vacant orbital here. So 1, 2, 3, 4 and 5 and 6, sorry. So what I'll get? D2 sp3 hybridization. Now this D2 sp3 hybridization, if they form hybrid orbitals 1, 2, 3, 4, 5, 6, so I can write 6 D2 sp3 hybrid orbitals. Okay, now which is the ligand here? NH3 is the ligand here, so we will have NH3, you have NH3, like this you have to write in the exam. Okay, now these ligands will donate the electrons. So what is the hybridization? Hybridization is D2 sp3. Magnetic property, you can see here in the metal there is no unpaired electron. So what is the magnetic property? It is diamagnetic. Next, geometry. You can see whenever there is 6 coordination number, the geometry is always what? Octahedral. Okay. Moving to the next one, synergic bond in metal carbonyls. Yes, you have to draw the diagram and show the synergic bonding. You have to basically show which orbital to which orbital sigma bond is formed and how the pi bond is formed. Okay, so sigma bond is formed between what? The carbonyl carbon and the vacant orbitals of the metal. And how this the pi bond formed? Pi bond is formed between the filled d orbitals of the metal and vacant anti-bonding pi star orbital of the carbon monoxide. This is very important. Okay. Next, we have d orbital splitting, T2g, Eg, how it is splitted, that you should know. And very important, the levelings, the things that has been written here, the every marking should be done properly. Next, for the tetrahedral splitting also, you have to write down these all things, especially this is what is written at the bottom. Prepare accordingly. Okay. Next chapter will move to DNF block. Okay, so here are some important, I'll just solve one and others you can try. Calculate the magnetic moment. Okay, so what is the calculation of magnetic moment formula? Root over of n into n plus 2. What is n here? Unpaired electrons. So to solve this question, you should be very thorough with the electronic configuration. So if you have not remembered the electronic configuration of scandium to zinc till now, please go and remember that first. That will help you to answer a lot of questions, okay, in this DNF block chapter. So scandium electronic configuration is 3d1 4s2. Okay, scandium titanium. Scandium is 3d1 4s2. Now if I have scandium 3 plus, then all the electrons will be moved and I have only Ar left. So there is how many unpaired electrons here? For scandium 3 plus, unpaired electron is 0. So that means if I substitute here 0, magnetic moment will also be 0. Next, for example, Ti 3 plus is given. Scandium titanium. I'll just solve for titanium here. So titanium is 3d2 4s2. Now Ti 3 plus is how much? 3d 1. So 1, if I substitute 1 into 1 plus 2, that is root over of 3, which is equal to 1.73. Okay. Now let's go to the next one, formation of interstitial compound. So here you should know what is interstitial compound and what are their properties. So interstitial compounds, you know, when there is small gaps between them, and if there are some void spaces in that, small atoms get occupied, that is called as your interstitial compounds. Next, you have to write their features. Similarly, you have what are the catalytic properties of transition elements, why they show catalytic property. You have to remember any 1 or 3 points minimum you should remember, because this can be asked in a 3-marker question. And then the examples, certain examples you should know. Next, composition of mixed metal and its use. This is very important. Use also you should remember. Next, I have potassium permanganate preparation. This is definitely, it is going to be asked either KMnO4 or K2Cr2O7. Any one preparation will be asked in the example. So please remember the reactions check it again from the book, remember it. With balancing, how to balance also you should know. Similarly, next we have the preparation of K2Cr2O7. Properly you have to remember this also. Now coming to the next one, we have what is lanthanide contraction, cause and consequences. So first of all, you should know what is the definition of lanthanide contraction. The steady decrease in the size of the atoms from lanthanum to lutetium or along the series is called as lanthanide contraction. Why does it take place? Due to the poor shielding of 4f electrons. What are the consequences due to lanthanide contraction? The size of 5D and zirconium and hafnium size is almost same and it is difficult to separate them, and the basicity decreases of lanthanum to lutetium hydroxides. Okay, so here you have to mention hydroxides. Okay, next, actinoids, why it is difficult? Three things you have to know. First of all is their radioactive elements, half-life is left very less, and they are prepared in nanograms. Difference between actinoids and lanthanides, this is a very rare question, but still you can remember 2 to 3 points here also. Next, this is very important question, why Cr2 plus is reducing and Mn3 plus is oxidizing when both have D4 configuration. So if you see, let me just first explain this one. Cr2 plus has D4 configuration, Cr2 plus moves to Cr3 plus. Okay, why Cr3 plus? Because here it is D3 configuration, T2G configuration, which is very stable. Now when it is going to +2 to +3, it is actually undergoing oxidation. So it will behave as what? Cr2 plus will behave as a reducing agent. Now if I talk about Mn3 plus, Mn3 plus goes to Mn2 plus. Why? Because here it is D4 to D5. Now what is special about D5? It is half-filled configuration, right? So Mn +3 to +3, it is undergoing reduction. If it is undergoing reduction, Mn3 plus will behave as an oxidizing agent. Okay, that is the reason. How will you explain it? Cr2 plus is reducing because its configuration changes from D4 to D3. The later has a half-filled T2G level. And Mn +3 is oxidizing because the configuration changes from +3 to +2, resulting in the half-filled configuration which has extra stability. Next, why is the highest oxidation state of the metal exhibited in the oxides of fluorides only? So that is because, why? Both oxygen and fluorine are highly electronegative and are very small in size. Due to these properties, the higher oxidation states are stabilized by oxygen and fluorine. Next, which is a stronger reducing agent? Cr2 plus and Fe2 plus. Reducing agent Cr2 plus and Fe2 plus means they will reduce others. Itself they will undergo oxidation. So if you see Cr will undergo oxidation to Cr3 plus, right? And Fe2 plus, if it is undergoing oxidation, Fe3 plus. Cr3 plus, just now I told D3 configuration, T2G3, Fe3 plus D5 configuration. Now the question is, out of D3 and D5, which is more stable? You might be thinking that D5 because it is half filled, but now since you have already studied coordination compounds, you know that when T2G is something which the energy goes down, like the energy level splits and T2G level goes down. So T2G level is lesser in energy and more stable than D5. So because this is more stable, this reaction will occur faster, or this oxidation will happen faster. So Cr2 plus will be a stronger reducing agent. Okay. Yes, you can see here Cr2 plus stronger reducing agent than Fe2 plus. This is because the configuration of Cr2 plus changes from D4 to D3, and D3 is stable due to the half-filled T2G level. Okay. Next, we'll move to chapter number 5, I think, haloalkanes and haloarenes. So in haloalkanes and haloarenes, first of all, for 2 marker section, you should be very thorough with all these name reactions: Schwarz reaction, Finkelstein reaction, Woods reaction, Fittig reaction, Woods, Fittig and Sandmeyer reaction. These 5 reactions you must remember in the exam. Okay, I'll be telling you in just let us discuss all the reactions in short. So first, whenever you write the name reaction, 2 things you have to follow. First point is the definition or about the reaction. In this definition, there should be 3 things. What are there? Reactant, reagent and product. You have to write this changes to this in presence of this one, that is called as this particular reaction. So for example, if I want to write for Schwartz reaction, I'll write alkyl chlorides or alkyl bromides are converted to alkyl fluorides in presence of metallic fluorides such as AgF, SBF, something you can write down the example, and this reaction is called as Schwartz reaction. The second point you need to write is example. Okay, so you can write CH3Cl plus AgF gives you CH3F. Okay, so that is there here. Next, we'll talk about Finkelstein reaction. So Finkelstein reaction, let us follow this method. What happens? Again, alkyl chlorides or bromides are converted to alkyl iodides in presence of NaI and dry acetone. So that is my Finkelstein reaction. So you also have to write the reaction here. So I can write like this: CH3Br in presence of NaI dry acetone, it gives CH3I. Okay. Next we have Woods reaction. Okay. Woods reaction is what? Woods reaction is the reaction between, you can write down, alkyl halides react with each other in presence of dry ether to give you alkanes, right? That is Woods reaction. Next, what is Woods? We can write after that, what is Fittig reaction? Aryl halides react with each other in presence of sodium and dry ether to give you diphenyl. Then what is Woods-Fittig reaction? Alkyl halides and aryl halides react with each other in presence of dry ether, sodium and dry ether to give you aryl, just you can mention, they'll produce you aryl alkanes, right? So that you can write down as a Woods-Fittig reaction. So I've given an example, you can follow the same method for all of them. Now, why the preparation of aryl halides by Sand-Meyer reaction? Yes. So what happens here? Aniline reacts with dilute nitrous acid to give you benzene disonium chloride. Now, benzene disonium chloride reacts with CuCl or CuBr to give you chloro or bromobenzene. Okay. Next, what is Saitzef rule, and give an example. So according to Saitzef rule, what happens in dehydrohallucination? More substituted alkene is preferred. To write the rule and then one example you can give here. Next question, aryl halides are less reactive. So there are three reasons here. Very first one is resonance effect, that is the partial double bond character is there. Next is the hybridization, sp2 hybridized carbon, and third one is the phenyl cation or instability of phenyl cation. Next we have write the SN2 mechanism. So SN2 mechanism you have to show here. Then write what is racemic mixture and represent the butanol in the form of racemic mixture. So racemic mixture is what? A mixture which contains two enantiomers in equal proportion and have a net zero net zero optical rotation. And how do we represent anything? So with plus minus butane 2-oil if you write, that is how you are representing a racemic mixture. Next question we have write the mechanism involved in the conversion of 2-bromo. So this is SN1 mechanism. So SN1 mechanism in 2 steps you have to write down. What is enantiomers? Non-superimposable mirror images. Name one physical property which differs in the enantiomers. The physical property is what? The way in which they rotate the plane polarized light. Moving forward, we have what are freons. So freons are chlorofluorocarbons, and here you should remember, name the poisonous gas evolved when Cl2 is oxidized. So that is phosgen, and here you should have to remember a particular freon, that is CCl2F2. Now this is produced using Schwartz reaction. Okay, so please remember this one, important one. Next we have 3 differences between SN1 and SN2. You can write any 3 difference. Next, identify A and B in the given reaction. So here what is happening? Okay. So first of all, here I will get a benzene disonium chloride. Right. Now B, what will happen? Here bromine will form if you use Cu2Br2. Okay. That is formation of bromobenzene. Moving to the next chapter, alcohols, phenols and ethers. So some basic, this is a very big chapter. Be very selective here and study these questions definitely. Okay. What are the reactions involved in the preparation of phenol from cumene? Okay. So cumene to phenol, very important reaction. First you will get hydroperoxide, then OH, and then CH3COCH3. Next is Williamson ether synthesis. So any particular example you can take. What we have to exactly react? Methyl chloride with sodium ethanoate. Okay. The question is asking preparation of methoxyethane. So how will you prepare methoxyethane? So you have to take one alkyl halide and one alkoxide ion. So if you take methyl chloride with sodium ethanoate, that will give you this one. I'll write the reaction and I'll show you, just a minute. So I have methyl chloride, okay, plus I have CH3 CH2ONA. Now that will give me what? This O minus is there, it will attack on this one, so it will give me CH3 CH2O CH3. Okay, so this will give me methyl ethanoate, or you can say methoxyethane. Equation is already there. Next we have complete the following reaction and name of the reaction. So this one will give you Reamer-Tiemann reaction or salicylic aldehyde, OH and CHO. What is the name of the reaction? Reamer-Tiemann reaction. Just check the spelling and write it correctly in the exam. Next, how do you prepare alcohols? By reducing carboxylic acid. So when carboxylic acid are treated with lithium aluminium hydride, we get alcohols here. Okay. Next we have how do we convert the following? Okay, so butane 1-OL to butane 1-oic acid. So directly if you want to convert primary alcohols to acid, you can use KMnO4, very strong oxidizing agent, or K2Cr2O7. Next you have cyclohexene to adipic acid, that also you can use KMnO4 dilute H2SO4, you will get adipic acid here. Now next question I have is, while separating a mixture of ortho and para nitrophenols by steam distillation, name the isomer which is steam volatile and give reason. So all of we know here ortho nitrophenol is steam distillation because here we have intramolecular hydrogen bonding, whereas in para nitrophenols there is intermolecular hydrogen bonding. Okay. Next question is explain Cole's reaction. So again the same name reactions, you have to write the definition and then you have to write the reaction also. Next we have some other name reaction, Reamer-Tiemann reaction, again statement and the reaction for that one. Next we have some mechanisms, 3 important mechanisms is there that you must be revising. The first mechanism is here conversion of alcohols to alkenes. Okay, this reaction mechanism. So see, the 5-marker questions will not be directly any 5-marker question, it will be 3 plus 2. Okay, 2-marker questions which I have discussed previously, that will be coupled with any of these 3 mechanisms most probably. So alcohols to alkenes, how it is converted? Step 1 is the protonation of alcohol, step 2 is the formation of carbocation, and then in step 3 there is a elimination and we get an alkene formed here. Okay. Next mechanism, that is dehydration of alcohols into ethene. So that we have already discussed now. Explain how anisole reacts with acetyl chloride. Okay, so one second. Okay, dehydration of alcohols to ether. This is another mechanism that you should focus. So that is, first of all, dehydration of alcohol can either give you alkene or ether. Okay, so ether, how the first step is same. Here it gets protonated. Then here we have, after once it is getting protonated, in that case, in the dehydration of alcohols to alkenes, there the second step was dehydration, or the water was removed and we were getting a carbocation there. Here in the second step what happens? Another molecule of alcohol attacks to this protonated alcohol and this one attacks here and then one H plus goes here and finally there is deprotonation. Okay. Next one, how anisole reacts with acetyl chloride. Okay. This question, you have anisole. Okay, acetyl chloride. Now this is ortho para directing. So what will happen? Acylation will take place at ortho and para positions. So what you will get here? You will get OCH3 and I'll get COCH3 here. That is one product, and then you have this one OCH3. And at the para product you have OCOCH3. Okay. Next, we will have another mechanism, that is mechanism of alkenes to alcohols. Okay, alkenes to alcohols mechanism also you should know. So first of all, there is attack of nucleophile. There is a carbocation formed here, and after that water molecules are added here, so you'll get a protonated alcohol, and finally there is deprotonation. Okay, so these three mechanisms you have to follow. Now, so once again, if I just want to summarize, in chapter number 1, that is in haloalkanes, okay, and haloarenes, two mechanisms you should focus. One is SN1 and another is SN2. In case of alcohols, phenols and ethers, there are three mechanisms. First one is alcohols to alkenes. Okay. Next is alcohols to ethers. And this one, third one, is alkene to alcohol. Now please remember, students get confused with these two, okay, and this is less important. As this is less important, these two are very, very important. Majorly these two will be asked, so be very careful whether alcohols to alkenes or alkenes to alcohol. When you prepare it, keep it properly in your mind what exactly you are doing. Okay, now let's do the next one. We'll go to the last chapter, electrochemistry. I have kept it in the last because a slightly difficult chapter. So first you should revise all the easy chapters. Now here there is one law will be asked. So definitely here directly 3-marker questions will be asked. So you can Faraday's first law and second law you should remember, and its mathematical equation. Okay, so first law is what? The amount of chemical reaction depends on the amount of current passed. What is Faraday's second law? Faraday's second law says you that when the cells are connected in series, when you pass same amount of current to both the cells, the mass deposited on one cathode to the mass of deposited to the another cathode will be equal to the ratio of their equivalent weights. Okay, so that is there. Next we have the SHE. This is very important question. Every year SHE question is asked. Okay, so you have to first explain the construction of SHE. This is important. Working principle is not asked. Okay, this is not important. Then you should know how it is notation and its representation. Okay, so first let me tell you what is SHE. The standard hydrogen electrode consists of a platinum foil coated with finely divided platinum. The foil is connected with a platinum wire with mercury. A copper is connected from mercury. For external circuit, the platinum foil is dipped in 1 molar HCl concentration. Okay, so this is what? Yeah, this is the diagram you have to draw, and this is the working not construction that you have to write. Now the next important thing is how it is denoted. How do we represent it? Okay, so it is represent like this: platinum H plus H2. Okay, next is what? The reaction that happens here. So reaction is what? H plus plus 1 electron gives you half H2. Okay. Moving forward, we have neat level diagram of hydrogen oxygen fuel cell and write its anodic and cathodic reaction and the overall reaction. These all questions are very important and can be asked. Now this question is recent, I can say trending question, like last year in midterm of different districts, and in the final exam in the sample question paper also this question was there. Why we cannot measure directly the resistance of an electrolyte? The two problems you have to write and two solutions you have to write. The first problem is direct current can change the composition. The second problem is solutions. Because electrolytes are solution, you cannot connect it directly to the Wheatstone bridge. So what is the solution for the first problem? Direct current can be replaced with AC current, and for the second one, instead of solutions, we can use something called as conductivity cell. Inside the conductivity cell, you have to put the electrolyte, and now this conductivity cell can be connected to the Wheatstone bridge. Moving forward, we have plot a graph of molar conductivity versus a concentration for strong and weak electrolyte. Okay, so this is very simple. Oh, just a minute. Yeah, so you can just draw here for strong and weak electrolyte. This is the graph. This is the graph for strong electrolyte. and this is the graph, sorry. Okay, this is the graph for weak electrolyte and this is the graph for strong electrolyte. And this side we have molar conductance and this side we have root over of C. Okay. Next, for strong electrolytes, write the equation that represents. So this is your D by Huckel equation. Lambda m is equal to lambda naught m minus A into root over of C. Okay. So this is there. This is the, so students, please remember, this is a passing package video. Means electrochemistry I consider is a difficult chapter, so you have to focus on other chapters more. So that is why here some of the easy theoretical questions I have given. Okay. Now if you want to prepare more electrochemistry, you can watch my video on I have done a detailed like the midterm series rapid revision 2+3 markers question. In that I have taken all the difficult or all the numericals of electrochemistry. You can watch that video, or in our, if you just go to the live section, there also I have given questions on electrochemistry numericals part especially. You can also learn from there. Okay, so here in this video I have not included numericals knowingly because that is slightly on the tougher part, and this is just something, the basic things that you must need to cover before exams. Okay, I hope this video was helpful. If you have any further doubt, please put down in the comment section, and please remember, if you just study this much, you can definitely score very 40+ marks. You can definitely score. So please start preparing, watch this video, learn all the answers and then go for the exam. All the best and thank you.